Morning, afternoon, everybody. Welcome. Thanks for joining us for our latest webinar. As I hope you're expecting, today we'll be discussing how to fit MET models with complex variance structures. We are joined once again by Dr. Salvador Gezan, and he'll be demonstrating a workflow for both single and two-stage analysis. If you've got any questions, pop them in the chat, or you can pop them in the question and answer section. We will attempt to get to them at the end of the webinar. If there isn't time, we will address them in the follow-up. We'll send you a follow-up email with answers to the questions, and it will also include a recording of the webinar. Do feel free to send a hello in the chat, let us know where you're from, what you're expecting out of today. And without further ado, over to you, Salvador.
And hello, nice to be here again. Good morning, good afternoon, or good night, depending on what time you're in. So today I'm going to talk about MET analysis. I'm going to bring a data set that is relatively simple, but I want to illustrate different capabilities of how to fit an MET, and also a few things of my personal tricks or my personal approach of how to analyze this data. I'll start with the single stage analysis, where we put everything together and we try to get the full analysis in one. And then I will explain a little bit later on the two-stage analysis and some of the libraries and some of the routines we have for that. So let me start sharing my screen. And I'm going directly to the, I'm going to go directly to the MET analysis. Let me just go to the beginning. So again, that's my contact information. And so again, if you need me for something else or some questions related to this, you can always ask. So why do we do MET analysis? Obviously, it's because we have several trials or experiments where we want to combine into a single analysis. This is obviously what we do when we evaluate varieties across different sites, environments, or years, and even sometimes treatments. And often the overall goal is to obtain a single breeding value or a single total genetic value of the varieties across the environments. In some cases, we want also the specific genetic values by environment, so we can post-process them in a different way. When we do this MET analysis, we have a better understanding of our GxE or G by year. And this is quite relevant because it helps us obviously to define some elements of our breeding program, such as the strategies, or to get subpopulations or sub-geographical areas where we're going to do our selections, obviously understand part of the dynamics of some genotypes and the interactions, etc. Now, one of the things that we look at as a quantitative geneticist a lot is with the MET analysis is getting these correlations of site to site to understand again, the correlations between the genetic values. And the analysis we do also allows us to estimate heritabilities, and in this case will be unbiased heritabilities because we isolate the GxE from our genetic signal. So it's not an easy analysis. You probably already have some experience with that, and there's a few things we need to kind of look at, and obviously we have sometimes hurdles that we need to address. One of the main things that happens with the MET analysis, and there is something common that you have to really see, is that you need some connection between the sites or the environments. And this means having some genotypes replicated on more than one site. The connection doesn't have to be perfect, which means not every genotype has to be in every environment, but there has to be some connection between them. Remember, you're estimating a correlation across genetic values between two sites, and that means you need to have genotypes that are in both sites. This is a bit different when you have the pedigree information, which doesn't have to be exactly the same genotype, but you still need to have some connection, which means parents that are common between one environment and another environment. One of the other difficulties that occurs is usually when we pull data, historical data, is that we have sites or environments with their, I call it personality. So they were done years ago, or they were done with a specific design. They have a specific issues. Maybe the error structure is more complicated. There was maybe treatments or sub-treatments and so on. So you need to respect that personality of each design, which means that you need to look at each individual site before you combine them into a single analysis. And that's where this complicated or complex structure comes into place. There's a few things about the data on putting together the data to do this single analysis, being one stage or two stages, which really means we are estimating a lot more variance components, and the linear mixed model will obviously struggle. So starting values is a good idea. Simplifying the model in some senses, it's another good idea. And that's where the two-stage analysis comes. And keep in mind that you're always going to have some convergency issues, except when you deal with 3 or 4 trials and everything very clean and with good connectivity. Otherwise, you're always going to have some difficulties. You have to go back and reiterate, eliminate elements, put starting values, and so on. Another thing that goes with these lines is that preparing the data is a little bit more complicated than when we did the single site analysis, because we need to, for example, have a common incomplete block column across several trials, and not all trials have incomplete blocks, so it's missing in some parts, but also the recording has to be kind of congruent across the different environments. So there is a little bit more preparation on the data, verification that, again, that the response variables are in right order, that the missing values that you use in one trial corresponds to the same definition of missing values, and so on. So I'm going a bit long with that, but that's what it happens.
Before we start the next slide, a very quick question, but I think it might be relevant.
Yeah.
Somebody's asked what the optimal percentage of an environmental connection would be. Is there an optimal percentage, or does it depend?
So I tend to think that the minimum number I will use, my question is, what's the minimum number I will use of individuals that are common between 2 sites? Because you're estimating a correlation. So just think like a normal correlation. So if you have 10 genotypes across 2 environments, that for me feels to be like the minimum, to have 10 genotypes. But if you have a pedigree, or you're using a genomic relationship matrix, then it's a lot looser, because you're using the relationships between the individuals in different sites. And that could be much stronger in many cases. So in some cases also, you don't have connections and you have to come up with a little bit of a simplified model. So, but normally I will say 10. Okay.
Thank you. Hope that answers your question, Matthias.
Good. So the other thing is about when you're getting ready for the MET, besides all the checks and the things that I just mentioned, there are some things that I like to separate it as a priori. One of those things is to understand what happens on each experiment. You need to know their blocking structure. You need to know how they were established. Is this P-rep? Is this randomized complete block design, alpha design, and so on? If you are designing your experiment for an MET, you obviously need to consider all the traditional elements of randomization, replication, and control to define your experiments. So that's fine. But then again, once more, you have to make sure there is connectivity. This is before you do your MET analysis, but also when you're planning for an MET in the future. So make again sure that you have some form of connectivity. Now, once you get your data in your hands, that's a little bit different. Sometimes there's issues, but again, as I mentioned, you make sure you understand what happens on each of these designs. And I like to maintain the same blocking structure for each of the designs that it was defined with. So if it's an incomplete block design with replications, I will respect that. I will also look if there are some covariables that need to be used. And sometimes you have treatments here or treatments there, or things about like dates of planting and so that you might want to use. Again, that's something to try to kind of unify all your information. One thing I do a lot is implementing a post-hoc blocking. So sometimes you have trials that have poor precision, and you can superimpose some post-hoc blocking that kind of helps to do some spatial control. And also, obviously, to do all this spatial analysis of your field trial. So you have the access to the XY coordinates, then obviously you want to do a spatial analysis of each of these trials, regardless of the original designs, if you can. So all that allows you to recover information. So again, what do the strategies for MET analysis? And again, these are kind of my strategies that are a bit generic, but you can modify and use them in different ways for your analysis, depending on your objectives. So obviously, the first step is a careful cleaning process. And this again goes to redefine some factors, make sure the scales of the response variables are the same, the missing values are the same, you look at the range of the values and so on. So for me, it's like putting all these data sets one on top of each other and making sure that the columns are well defined and there's no inconsistencies. Then you analyze every site individually. So this is where you spend a lot of time looking at each site and seeing, for example, which one are the original design effects, and if you can add some other post hoc things to improve, that's where you do the spatial analysis. And you look for outliers, you look if they have some issues, and again, you look for spatial trends if you're doing a spatial analysis, and so on. Now, you calculate a heritability, and here is where you decide if, for example, some sites maybe have too much CV, coefficient of variation, and something off from them, or you might look at the heritability, and let's say your trait has a heritability of around 0.5 and this site has a heritability of 0.1. So there is something going on. You might want to decide to eliminate some sites because they are not adequate. Then you start combining everything together. Now I have this evaluate implementing data standardization because all days, and it's still done in some cases, some people standardize their response variable by site, and then they do a simplified one-stage analysis. Usually this is standardized by the phenotypic variance. And it's an approach that works well, allows to produce a number of variables to be measured. Sometimes you have controls, and then you have to kind of rescale in reference to the controls if you're thinking about diseases and things like that. So all that is valid, and this is the moment to think about it. Evaluate which covariables or you might want to add. Often we want to have something. Sometimes you screws, companies, and so on, or time of the year, etc., that you want to add as an extra factor. And then you start combining everything into a single analysis. And this is where you go step by step, baby steps I like to do. You first start with a single model, usually an interaction model that I'll explain what it is. And then slowly you add more complexity to your model. Even sometimes you leave some random terms out. You might, for example, have plot effects. You might want to leave those out. Or you might have some random effects that at the beginning you might want to not leave there or put as fixed effect, and then you move them slowly to random and so on. And one thing that is important to always keep in mind is that, especially if you're dealing with lots of sites and with very messy data, think about that you might even have some negative correlations between sites because things change over time, or you're going 10 years ago. Sometimes you have to favor a simpler model. And maybe it might not even converge the model, and you have no choice but to kind of make some terms much simpler and less specific by site. Or in some cases, assume that you have to use a common correlation across all environments, because that's the only way you can do this. Okay, so I'm going to start with a single site analysis of some of my data. And again, as I mentioned, this is just a single site analysis that might have some fixed effects, some random effects associated with the design, some covariables, the random effect associated with the genetics, with or without some genomic matrix or pedigree-based matrix, and then some error structure that often I would prefer to use some spatial analysis structure. Again, I want to respect everything from this analysis. So let me just go to the R code. Can you see my screen there? Hopefully, yes. If not, screen. Okay, so, and let me actually, one thing I'm going to do is, I didn't make the font a little bit bigger so everybody can see better. So I'm just going to load the library ASReml, and there is a play data set that I have in the library ASRml, which is the one I'm going to use. This is the phenotypic data from a wheat study, which you can see on the right here. The description of the study is originally 8 locations. This is in Nebraska and the US. And most of the trials have 2 replications, but there's a few trials that have a single replication. So actually 1 trial has 2 replications. All the other 7 have single replication or rep block, and everything is done as incomplete blocks, so sort of alpha lattice designs. And we have a total of 270 test lines that are being evaluated, plus 3 controls. So I'm not going to analyze all the data. All the data has a total of 8 sites, but I'm going to only use a subset of 4 kind of to illustrate a few of the things, and then I'll come back to all the data. So this is the structure of the data. We have location, we have rep 1 and 2, incomplete blocks, several incomplete blocks. A variable that identified which of the lines are identified as test lines or standards, identified as checked lines or standards, which is 1, and 0 identifies the ones that are just checks. The test lines. And then we have the positions for each trial, column and row, and yield, okay? So first thing, as usual, it's a good thing to do, define everything as a factor that you know is a factor. You might use it, might not use it. And also here, I'm defining 2 more variables, which is a row, which is a continuous row, and a continuous column. So I have row and column as factor, and I have them as a numeric variable, so I can use them in different elements for my analysis. When we do the MET analysis in ASReml, it likes things to be sorted. In this case, I'm sorting by column, then row, then location. So this is just to prepare myself. And I'm going to use the library ASR Trial that has a few auditing tools for METs. And again, this is only for locations. So in this case, I'm using the function audit MET. With the column associated with the trial is being equal to the location, genotype equals to gen, and response equals to yield. And what you can see here, it's a little bit of output. This is an incidence table that tells me how many genotypes in common I have between 2 sites. So this case tells me there is 269 out of the 270 plus the 3 checks that are common between these 2 sites. You can see all the numbers are very high. This is where you don't want a 0, or you want something that it's at least 10 that we were talking about before, that I said, how many do you want common to estimate that correlation? In the diagonal, you have the total number of genotypes that are in each location. This is eliminated the NA. So that looks pretty good, very good. I mean, this is a specific trial designed for this study. And here you have some summary statistics, like mostly we focus on the CV, but you might want to look at the ranges on the means, the ranges of the values on the response, and so on, to assess if those trials are okay or not. So this table is a summary table that tells me how many observations I have by rep, by site. And you can see here that the trial alliance has 2 reps and the rest has only 1 rep. And the next table is only the first few lines. It tells me how many plots I have per genotype. And you can see here, there's genotype that has 2. These are the test lines, and the first 3 are the standards or the checks. And you can see there's 10 plots for each of them. So that's pretty good. As you can see, there is lots of 1s here. That means that almost every genotype is on every single of these 4 sites. So first step, as I mentioned, this is do my single stage analysis, which is doing everything in one go. But before that, I start doing single site analysis for these 4 locations. So I'm going to use obviously ASReml and just show you a little bit of the code I have here. I have a very simple model, which is the overall mean. I have a rep. I have an incomplete block nested within rep, which I write like this. And I'm going to have my genotype effect as a random effect, incomplete blocks also as a random effect, and then my error. Now, my error is not that simple. You can see here, yield is my response, 1 rep, random. And the error I'm using is an autoregressive of order 1 to do some sort of a spatial analysis. There's plenty of literature that in the manuals of ASReml, there's more details. I'm not going to focus excessively here on the spatial analysis because the focus is on the MET, but I still need to do single site analysis. And this command here, subset equals location, is because I'm going to only pull the data associated with aliens. This runs relatively quick. And then again, what I do for each of these sites is you get a residual plot, check if everything is okay, identify potential outliers, check that your distribution again is close to a normal distribution, otherwise you have to decide to do a transformation and so on. Eliminate outliers that you find here. And this is very important to eliminate outliers early on the stage because they give you problems later. They are going to actually inflate your G/E when there shouldn't be because there's an outlier. Now, because this is a spatial analysis, we do a variogram. And then again, we want this to be as flat as possible. And this one has still a little bit of a structure. So my model, my spatial model, still failing into getting everything that happens there. A wall test in case you have other fixed effects that you add to your model that you want to test. The variance component, and once here you see the variance component of the incomplete block, genetic effect, the correlations, and then the final variance associated with that autoregressive structure. So pretty strong correlations on this particular trial. I can calculate a heritability, which happens to be the genotype effect divided by everything else, well, except the correlations. And you can see this is a very good heritability, 0.69. That's what we expect from this type of data with the smallest standard error. So very sweet and so on. Now, one thing I want to mention is that we have the checks, and I can leave the checks out of the estimation of the genetic component. And this is just to illustrate. I have, in this case, 20 plots on this particular trial from the check, which is 30 observations. Overall, I have 150 checks. But what we do is we extend this gen that we had in the model before to say, I only want the ones that are the test lines associated with this variance. And if you're familiar with ASReml, you will see this add check. So this add check, what it says, only give me the gen variance or the gen effects, if you want to think about it, for those individuals or for those elements on which the check column is equal to 0, which means the test lines. So this is what it's doing, is leaving out the standards. So, and then notice that I add the same term here, but I change the 0 to a 1 as a fixed effect. So in this case, you say the checks are going to be defined as a fixed effect on the fixed part. So they obviously don't contribute to anything. So we can see what their mean values are. Now, this is very important to understand this add check because it's subsetting this variance component, because later on we will use it to say, for example, at site 1, I want to have a rep effect, but at site 2, I don't want a rep effect because the design is another design. It's a completely randomized design, for example. So it's important when we pull everything to know that the add is giving us that extra flexibility, okay? So I'm going to run this. The model is going to have different log likelihood values and so on. The variogram is going to be a little bit different, but not much. Now, the wall test is going to identify the checks. So this is 4 levels. So it's 3 degrees of freedom. The 3 checks plus the rest is the 4 levels, and it's highly significant. Now, what's important is that these variances change. Now I have 69.12, and before going up, I have 70.41. So it reduced a little bit, and this is not uncommon by using these checks. Now, there's 2 schools that says because they have so many replications, they're not going to be shrink. So it doesn't matter if we treat those standards as fixed or random, so we can leave them there. And some people say, no, you have to take them out because they belong to a different population. They have to be present on the analysis, but they don't belong to my population of test lines. Again, depends on the specific problem if you decide to leave an in or out. In my specific case, just for illustration, I'll leave them out, but remember, we can leave them in. So the next thing is, and this is just before we get to the MET, is that I can do many other spatial models. I can add different random effects for controlling for rows within rep, columns within rep, trends, splines, and so on. Now I add in this particular analysis a random effect of row within rep and column within rep to get rid of that trend that we have on the right. This needs a little bit more extra iterations. And let me show you the variogram. You can see there the change from a small pattern to almost no pattern where everything is kind of flat. So this model almost didn't change on anything, except that we have a few more terms. The correlations tend to go down, particularly the one for columns. And my heritability changed very slightly, 0.69. And I think before I had also 0.69. Where is it? 0.6921, and now I have 0.6954. So really not much of a difference. So now I can kind of combine all my my analysis and everything together. Okay. So one of the things I'm going to do again after I'm supposed to be doing this for each trial, and actually I just want to show you what happens if instead of Alliance I use Lincoln IM. And this site is asking for more updates. You will see that the variance component, it is Lincoln IM, is still asking for more. It's saying that it has degrees of freedom 0 because that trial doesn't have the rep effect. So I need to make sure the rep effect is not there. And she says some components change more. And then here is giving me again some of the components associated with it, but you will see that the heritability is a lot lower, 0.38. Okay, so this is one of those trials where everything is much higher than this. We have a question, I think.
Yeah, that's right, Salvador. We've got a couple actually, if now's a good time.
Okay.
Hopefully quite quick ones. There's a bit of discussion in the chat about, excuse me, if MET is applicable or suitable for non-replicated trials. Do you have any thoughts on that?
It is suitable for unreplicated trials, but you have to be careful that your focus on unreplicated trial is not so much on estimating a breeding value or a genetic value by site as much as estimating a breeding value or genetic value across all the sites.
Mm-hmm. And another question, and probably again depends, but asking when we define blocks as fixed and when we define them as random.
That's a big question. And
yeah.
In this case, I have 2 replications only. So defining that as a random effect will give me 1 degree of freedom for that variance component to be estimated, which is a bit of a problem. You need probably at least 5 degrees of freedom to estimate a variance component. So that means 6 blocks. So in this case, normally reps will be fixed. Some people like them random because they define a population of blocks and so on. But my choice, particularly in this case, was fixed.
One more, because it's a follow-on from the first question. Mm-hmm. If there's no replicated effect, do we just need to remove rep.row and just fit row?
It will give me exactly the same analysis. So in this model, because location Lincoln IM has no rep, this is not going to cost me anything because the level of rep is just 1 and IBQ will go 1 through 20, for example. So I could write that, or I can write this like IBQ. So because it's actually identical, there's not going to be any difference in this particular case. Okay.
Perfect, thank you. There's a couple of others, but let's continue for now. We can pick them up at the end.
So one thing I wanted to show is this is the results of the analysis for these 4 trials. And it's important to make sure your data is fine for the pre-analysis of individual site. You see error variances 29, 37, and there's this 89 for Lincoln IM, which has the lower heritability. You have to assess if that's reasonable or not. But having the variance components here also allows me to have the the starting values when I got the analysis. So I have an idea what the error variance is, what the genetic variance is on each of the sites and so on, and I can use those for my analysis, okay? So I'm going to go from my single analysis into an MET analysis now, and there's two definitions of the MET analysis, what I call the interaction GxE and the nested GxE. So the GxE as interaction effect is really the same model that we have where we have yield, site, genotype, and I have this interaction site genotype. This is what we learn in our statistical courses as the model with A plus B and A 2 dots B. By the way, this should be 2 dots. And it's a very simple model, but notice that also that I'm doing something more is I'm allowing every site to have its own residual variance. And this is very important because the sites don't have the same heritability. So if you say you want only a single residual term, then you're forcing the bad sites to be as good as the good sites. And the good sites actually are going to be worse. So you are really doing what I consider incorrect weights for your calculations of your breeding values or genetic values later. So that's one thing that is important, and ASReml is flexible enough. This model always will fit, as many sites as you might have, but notice that it gives you a genetic effect and it gives you an interaction or the deviation of the genetic effect. And often, if you're only interested in the genetic effect, this is a really nice model. Assumes that you have a single correlation across all sites and assumes a single variance by site, okay, single genetic variance by site. But this model was used always, and this is how I learn my statistics. My advisor used this one, and then also this model will always fit. In contrast to that one, we have the nested model, where what we do is we get rid of this genotype effect, and we put only this term, site genotype, which in reality means genotype nested within site. And this genotype nested within site, we need to model what happens with the correlation between the sites. And this is where I used a core GH, and this is the beauty of ASReml. A core GH means a generic correlation structure, but you have other structure. If you're familiar with SAS, you have the UN or the US for ASReml, that's an structure. You have a core B and so on. Now, the beauty of this model is that it will allow me to have heterogeneous variances, which means a different variance by site, different genetic variance by site, and different pairs of correlations between all the pairs of sites. So in reality, it's allowed to be very flexible, with the caveat that you're estimating a lot more variance components. So this is not the adequate model when you have, for example, 10 sites or more, actually more than 5. But because I'm doing this nested effect of genotype with site, it allows me to have an effect of genotype on each of the sites, and then I can pull them together and average them and get my mean value of the genotype, or I can pull portions of the sites and so on, okay? So, and these are two examples of these correlations, which is what I'm going to do now. This is the core H, which is a different error variance by each site, different genetic variance by site with a common correlation across the sites, which in some analysis, this makes sense. If you want to be a lot more flexible, you say there's a correlation between site 1 and 2, correlation 1 and 3, 1 and 4, and so on. So you're estimating 10 variance components here, you're estimating 5 variance components here. And you can imagine when you have more and more sites, this increases. So the challenge is to try to get this correlation. And this is what I want to show you quickly. I'm going a bit slow, but so what do I do first is I take my original single site model, so which is this yield, rep incomplete block, genetic effect, rep row, and rep column. And what I need to do is I really need to extend. So I'm just going to pull this portion to show you a little bit what happens. I'll just do it in here. So this model, obviously, it has to have the overall mean and it has to have location. And then you have location. Actually, you have rep nested within location. And then you have to keep extending the model. You have location, rep incomplete block, you have genotype effect as a generic effect, but then now you add location genotype effect. So which is going to be my GxE for the simple interaction model. But I also need a location rep and a location column. So now there is a few caveats here that I'll come back to define, but one of them is that not all the locations have rep. There's only one location that has rep, and I can put a 1 to identify the first level, or I can put the name of the level, which in this case is alliance. So I'm just saying for alliance, give me the rep effect, not for the rest. Something similar we have to do with the rep incomplete block, because there is a variance of incomplete block within rep that is different for each location. So I just write at location here, which in reality what I'm doing is I'm allowing each location to have a different incomplete block effect. And so on will have to be for this term and so on for that. Okay, so I'm just going to jump to the actual code where you can see the same thing, location at location 1, the location and so on, and the genotype effect plus the genotype-by-environment. And notice here that I'm using this dsum to allow each location to have its own autoregressive structure. Okay, so I'm just going to comment this out because I never finished that. But when I run this, you will see it takes a little bit of time. It's a bit more data. There's more variance components. Sometimes you need a few extra iterations. You had a wall test associated with all the terms of your model. This is location, which is highly significant. Rep effect within one location is highly significant. And the variance component, which is what I just described, with rep effects, column effects, row effects. And this is my G, and this is my GxE. And I can actually calculate the type B correlation by adding the genotypic effect plus the sum of the two. Now you can see here, each side it has its own error structure, its own correlation. Some of them are very close to 0, some of them are higher, and so on. But you are allowing each side to express their own personality. Okay, so this is really what we want. I'm going to just take the correlation type B correlation by taking B13, which is this variance, and divided by the sum of 13 and 14. So this correlation is 0.799, which is very good. I can calculate heritabilities, but that's a bit more difficult. As you can see here, I have just made a single interaction model. I have put everything together, and that I could finish there. Now I can try to be more complicated and use the nested model. And in this particular case, I'm going to use the core V structure. So notice that what I'm doing here is I'm just taking, the only term I'm taking is genetic effect nested within location. Notice that before we have genotype and genotype location interaction, this is a nested effect, and I specify a core V. Now, a core V is a single variance and a single correlation. And it's as simple as the other one that we have before. Actually, the models are totally equivalent, and you get exactly the same results in terms of, I put an update. I didn't need an update here, but let me show you. The variance components are actually the same. But when you look at the correlation, is 0.799, which is exactly the same correlation. This represents this correlation here. And there's a common variance, which is 73.97, which is the average across all the locations. And the log likelihood values between the two models is the same. So this is just another parameterization of the same model. Why did I want to do that? It's because I want to show you the core GH, which is the more flexible one. Notice that in the core GH, the only thing I did is replace the core V by core GH. Everything else is the same. I gave it some starting values to help the system, okay? And this is not a bad idea, so it doesn't get too lost when it converges, because I'm asking for 10 variance components for the G part, plus 4 variance components for incomplete block, 4 for column, 4 for row, and 3 more variance components for each trial. So you can see here it's still struggling for some convergency. After a few times, you make it converge because what is changed is some of the parameters that have really values very close to 0. And you can see everything here. And you will see in this particular case, the variance component for the design parts. And this is the correlation between Alliance and Grandee, 0.90, Alliance and Lincoln, 0.63, and so on. And then the different genetic variances for each of the locations. So you're allowing everything to express in their own. And this is sometimes the model that most people are defending, to say, well, if you can analyze all your data together with their own personality, then it's just a matter of trying to kind of assist the mixed model routines to fit your model. Now I'm comparing here the core V against the core GH with a likelihood ratio test, which you use the function LRT ASReml. And this is highly significant, which means the model, the more complicated model, which is the one that has the core GH, is highly significant differently than the other one. So I should use that model. I just want to show you with this code just some of the correlations. What I'm doing is pulling the correlation, and this is the correlation between the 4 sites, 0.83, 0.71. So there is a good range, but it goes from 0.63 to 0.83. Remember, on the previous analysis, I assumed everything was equal to 0.79, and it's not the case. There's some differences. Okay, so one thing is what happens when you have more than 5 sites, and actually usually more than 4 sites, you get a complicated analysis and the things don't converge. So one option is to move from a core GH to a core H and assume the correlation is the same across the sites. And that loses a bit of a precision, but sometimes if you understand your breeding program, that makes total sense, because you know you have GxE, but it's not really that strong. And then you can say, okay, this estimation is around 0.8, like in this case, and you say it's okay to use an average, and it's not a bad thing. In other cases, you don't want to do that because you know some correlations go close to 0, and that means that you have to do something different. So one alternative is to use the factor analytic, which actually I use it as a way to approximate this core GH matrix. And the factor analytic is an approximation to that. It usually converges no problem, often doesn't need starting values because ASReml will define some starting values internally. And what it does is decomposes this G matrix into what is called loadings and then a specific matrix. So that's what I have in the next slide. So this 4x4 matrix, US matrix, is going to be decomposed in a factor analytic of order 1, which means it has 1 vector of loadings plus 1 diagonal matrix of the specific effects or specific variances called. And you can see this has 8 variance components instead of the 10 originally. You can go to order 2, and in this case, you're estimating 12 variance component, which you only need 10, which means 2 of them are going to be fixed. Now, this is very useful if you are saying that you have 10 sites. That means you need to estimate 45 variance components. Factor analytic of order 1 will estimate 20. Of order 2 will estimate 30, and so on. So you can use different orders and do that. So I'm just going to quickly show you that. I'm going to use an FA. Now, the only difference here is I replace the core GH by FA, and I need to add the order of the factor analytic that I'm going to use as an index there. So that's equal to 1. The model is using 8 variance components instead of 10. So that means these are my variance components, and the variance components give me the specific variances plus the loadings for each of the site here, and something similar you get for the genetic values. And look at the 2 likelihood values are different. And this is the FA, and this is the core GH. The FA is not as good as the core GH, but you can use some AIC or VIC to determine which one is better. And finally, it's interesting that when I use AIC, it tells me the core GH is better. When I use the VIC, it tells me the FA is better. I'm just going to use the FA. Now, one thing I need to show is you can reconstruct that correlation matrix by using those loadings. So again, this uses this mathematics of a vector times the same vector transpose plus a diagonal matrix, which is what I'm doing here. I'm constructing R, constructing L, summing everything together. And I have my G matrix based on the factor analytic, and this is my G matrix based on the core GH. They are similar, they're not identical, but they are similar. Okay, and obviously you can calculate standard errors associated to them, which is a bit tricky, but it can be done. So assuming I'm happy with my FA model, which in this case, according to the BIC criteria, will be better. In reality, there's not much difference between the two models. I can proceed to get my predicted values by genotype, by location, so genotype nested within location, or a genotype effect across all locations. And this is the ones I'm going to use to make my final selection. So here I'm getting a value, and you can see the beginning and the end. And let me make this bigger. You have, for each variety, you have on each location a predicted value with an standard errors based on this model. Even some genotypes that are not present on one site are going to have a predicted value because their sites are correlated, so it's going to manage to make a prediction, and you'll see much larger standard errors on those individuals that are not present in one site, but they have a prediction. And you can also get a prediction of the genotypes across all environments, which is equivalent to averaging the predicted values by location. And I can show you the beginning and the end. And here you can see the values of your commercial varieties against the test across all locations with their corresponding standard errors. So this is what you will use to make your final selection. Okay. So I know it's a lot of material, and I wanted to show you the two-stage analysis. And before I show you the two-stage analysis, this is an example of a code on which I allow each site to have different terms. So for example, I have an individual element for the rep on location 1, but I have a continuous row column that I allow it to be on only site 2. Sorry, a continuous effect of row only on site 2, a continuous effect of column on sites 2 and 4. All the sites have incomplete block effect, but only some of them have column within rep and row within rep. And also here, I allow for different error structures. Some sites have AR1, actually site 1, and 2, 3, and 4 are independent errors. So you can fit this one, as I want to show you this one because then it really, ASReml allows you to have all that flexibility of the models in just one single case. Again, this fits well because everything is well connected. In some cases, you have to provide starting values and assist the system so it converts, but I'm not going to show that, okay? So a couple of things. For the two-stage analysis, this is more like it's becoming a bit more standards because this is what is often used. The results from the first step from the two-stage analysis often used for genomic selection and for GWAS. So we did the single-stage analysis on which everything is in one go and no statistical issues. Everybody happy, really. That not usually the case. You have to fiddle. Somebody who knows has to put in the terms, eliminate terms, and so on. And as you can see before, there might be a few convergence issues whenever you have many more trials. But the factor analytic provides a way out when you have too many sites. Now, more standard, and this is also something more historical, is do this two-stage analysis in which we separated into the first step and the second step. On the first step, we did what we already did, which is analyze each site individually with their own characteristics and define which one is the best spatial analysis or which components have to be there. And we store something that is the predictions and the weights. And then on the second step, we pull the information from the first step into a second analysis that now doesn't need the, for example, random row effects or the random incomplete block effect or the spatial components. In the second analysis, we only focus on that G matrix for the G by E. And this is pretty much what I'm saying here. We use the first step to add all the fixed effects, random effects, and this is the adjusted values. And then we store the weights. And two definitions of the weight is one over the standard error of the mean or the prediction square. And then the other option is the variance-covariance matrix of the predictions. You get the diagonal and you get the inverse of the variance-covariance matrix of the predictions, and then you just store the diagonal of the inverse of that matrix. Both give you very similar results. And this is exactly what we normally tend to do, this sort of first step on the genomic selection or GWAS. And then we don't use the weights normally, but in this case, we want the weights. The weights will tell us which phenotypic mean that we have has more value, usually coming from sites with higher heritability than others. On the second step, we pull all that data and we do a weighted analysis, and we can use any structure we want. And then we only worry about the G because the R is already absorbed in the weights, okay? And then we get our predictions. So I'm going to go a bit quick with this. I'll use ASReml-Triala. And in ASReml-Triala, we put together an easy way to get those predictions and read the weights. And also ASR-Triala does some of the automatic single-site analysis. But again, you don't necessarily have to do it, but you can use ASR-Triala to guide you. So I'm going to read a matrix that has already the single step finished. So we have the same location, the checks, the genotypes, a predicted value, their standard errors, and their weight corresponding to this diagonal of the variance-covariance matrix, the inverse of the variance-covariance matrix of the predictions. And these are the weights I'm going to use. Notice also that some of them have much higher weight than others because they have more replication. So this is, again, this is very relevant. Not only come from maybe a better site, they also have more replication. So this is the data from one of the sites, and you can see one site has really very low value, so that might be an outlier. The ASR-Triala has this function called fitmet, which actually will read the data set. If you tell it which one is your column for the genotype, which is your column for your trials, which in this case is location, which one is your response, which one is your weight, do you want genotypes random or fixed? In this case, we want them random, and the trial or location to be fixed in this case, and what structure you want here. You can have 1, 2, or 3, whatever, FA, core, GH, and so on. Now, in this case, I'm using the 10 trials, okay, because I just pull all the data from the original data. So location, sorry, I'm using eight levels. So I'm going to proceed to fit this. Oh, I need to load ASR-Triala first. I did skip this part. So it just has a few message. Why it's not liking me? That's probably because of this. Okay, so it fit the model. One thing that is important is if we can look at the call from this, some of the objects of this is the actual model that has been fitted. I have my response variable, I have 1, my location, a random effect, I have an FA of location of order 3 with genotype, independent genotypes. If you want variance-covariance matrix, you can change this and run this call again. And then this is the very important part that tells ASReml that you have weights, and those weights are going to be considered. And also we say that the error variance is going to be fixed equal to 1, because we don't want to refit the model. We just want to use those weights, okay? So some of the variance components you will see here, an FA of order 10, of order 3, with the specific errors for the A sites, loadings for the first loading, the second loading, and the third loading. Everything seems to fit fine. I can look at some statistics like log likelihood, AIC, BIC, in case I want to compare an FA3 against an FA2. I do have my predictions, and these are the predictions of genotype by location. And again, I can pull those predictions to be across all the sites. This is the variance-covariance matrix of my FA. It's 8 by 8, but actually more relevant for us is the correlations. And you can see here correlations. What strikes me here is clay center has 0.45, 0.47, 62, seems to be, and even a 0.19, seems to be much lower correlation than what you see in most of the other cases of around 0.6, 0.7, even 0.8 in some of the cases. So that is the correlation matrix. We also have some of the loadings. And just for comparison, this is the analysis we did before with only 4 sites. And this is the analysis from this 2-stage analysis. The correlations are similar. They don't have to be identical. We're using 8 sites and so on. You can get sort of like a heat map from your sites. The sites are being grouped in a subset of 4 and another subset of 3 and one that seems to be off from the rest. This is the clay that I mentioned before. And you might want to use this to redefine your breeding zones and so on. ASReml-R also has Biplots. And this is one case. I mean, many of you are familiar to use Biplots to assist the selection. And actually, if I put the unit levels as true, we'll give you the names. And you can see Freeman here. This is actually the standard check use. And then you can see where it is in respect to the sites and the correlations between sites. One function that we have in the ASReml-R is some summary for the factor analytic. This one, what it does, it allows me to understand the GxE dynamics of each of the test lines. It actually starts by calculating how much variability, total genetic variability, is explained by each of the factors. In this particular case, you see 2 factors explain 61. Then a third factor just jumps to 65. You have these factors rotated, and also you can see how much the factor is explained by site. You have some site like clay center that is not very well explained by these two underlying loadings. And then again, you can look at some specific things by each genotype. And this plot is the GxE plot of the genotype, in this particular case, Freeman. The line, it's fitted line, is based on the parameters of the linear mixed model. But you can see this variety is quite high above the mean. The mean is around 50. It has a negative or a smaller value on one side, which this is the one that interacts a lot. And then you can see it tends to go up. And we can look at different varieties, and I'm just going to show you 2 of them.
Salvador, I'm just giving you've got a 1-minute warning before we...
Okay, no problem.
We've got a few questions as well. Sorry, I'm interrupting you, Salvador. I just want to let people know these questions will be answered in the email that we send out with the recording. So if we're unable to get to the questions today, please don't worry, they will still be answered. And I'm almost over. I just have 2 more things to show. This is a couple of the varieties, and you can use this type of plots to understand the behavior. These are underlying factors that we tend to think might be like some environmental covariable associated with them, maybe humidity, level of nutrients, and so on, and temperature, etc. So you can see this variety, it's relatively more or less flat on all the locations except this one. With some GxE, but it's high up, and this one doesn't like this factor and tends to drop down a little bit. And again, we have a high GxE associated with this, and we can try other ones. Just the final thing is we can also get stability plots in case you want to make your selection. These stability plots, let's see if I can get it, obviously allow you to select from a pool of different varieties. This is Freeman again. This is a very good variety, also on the top 3%, but it's a variety that has a high index, which means it's very unstable. And on top of this one, you have this one that is a lot more stable,
and it has a good yield. So again, you can complement this stability index with your results from the factor analytic, which is a lot more flexible. Okay, so I mean, again, this is not, I'm not presenting all the details of ASReml-R, but I'm just using some of the functionality to let you know that you can explore this complex GxE with different variance structures, particularly the FA that is more informative, but also a core GH that gives you the information you want. And if you need our help or my help on something, please feel free to ask questions today or just then shoot an email and I'll be happy to assist. Okay?
Brilliant, wonderful. Thank you so much, Salvador. We've got an awful lot of questions actually.
I imagine.
Yeah, we're not going to have time to get to them today. So as I say, to the best of our ability, these will be answered in the follow-up email. I imagine some of the questions are a little bit bigger than that and maybe the subject of our next webinars, which we'll give you details for. Just want to mention one thing, if you're not aware, ASReml-R is a free R package. It's an add-on to ASReml. You can download it from the VSNI website. We'll send you details again of that in the follow-up email. So apologies we didn't get to all of your questions. This was a particularly popular webinar. Thank you very much to Salvador and keeping to time, very informative as usual. Once again, follow up with the questions and the recording, and do feel free to get in touch with us in the meantime if there's anything specific that you'd like to ask about or discuss.
Thank you very much.